Hi, I'm Ben-Yaakov. This presentation is entitled Why Use an Insulated Power Supply for a High-Side Gate Driver. Let me start with some background here. Bootstrap arrangements are used to supply the power to high-side gate driver. They are very economical, very popular, and easy actually to implement. However, in this presentation I'm going to explain and demonstrate by simulation why is this method not really recommended for systems that are using fast transistors like gallium nitride MOSFET that run at high switching frequency. I'm also discussing some second and third order effects which are sometimes overlooked. So here is my simulation circuit for a Bootstrap. I have here the high side driver. It's a analog devices driver, which is nice because it's in the library of LT SPICE that I'm using. And here are two transistors. These are hefty transistors. We'll talk about it, 100 volt transistors. And then I have here a power supply of 12 volts. I've put here a resistor to limit the current when charging. And then we have here this floating capacitor. This is the Bootstrap capacitor, which is to maintain, or it's used to maintain power to the unit while this side or this high side transistor is at high potential. So this will be like the local power supply during this period of on time of this transistor. I've also put here a auxiliary circuit to generate the Q. This is the charge that goes into the gate, and this is done by taking the integral of the current of this resistor, which is the gate current, so we can see the total charge going into the gate. Okay, so this is the simulation circuit. So how does it work? When the midpoint goes down, okay, this midpoint goes down, this transistor is on, this one is off, of course, to avoid the shoot through. Then we see that we have a loop here, which is closed now. We have the power supply, 12 volt, diode, which is conducting and charging this capacitor, which is now connected to ground, to this ground here. So this is the charging phase of this capacitor. And then when the midpoint goes up again, then the voltage across the diode becomes negative, so it's sort of blocking, and it's off. And then the capacitor is responsible for maintaining the charge to the current to the driver and the charge to the gate. Okay, so this is the idea of the Bootstrap. So what is the size of the capacitance that we actually need? Now the capacitor has to supply two charges, one to the driver and then to the gate. Okay, now the driver, the quiescent current is something like 3 milliamp. Now 3 milliamp, but then it is drained during the all on time. I'm assuming that this has to do with the duty cycle, of course. I'm assuming like a maximum duty cycle, so it will be the period of the switching frequency. Now in our case I'm going to talk about 100 kilohertz, but in some application, the switching frequency is low, like 50, 60 hertz. So this time could be large, and therefore the amount of charge is not insignificant. Here, it's fairly low. So we have this part here, and then we have the part of the charge to the gate. Now, I highly recommend to look at this curve for the charge of the gate, not use like the equivalent capacitance or any other means. This tells the whole story. It says that when you drive the gate, you need that much of a charge to bring up the voltage to a given level. And this is, of course, for some operating condition. This is 100 amp, and VDD is here given for various voltages. I'm not going to explanation of this curve. You can find it in my YouTube channel. There are a number of videos explaining this flat portion, for example. Okay, so now taking these two numbers into account, I found that I need something like 0.15 microfarad. So I'm going to put 0.33 in the simulation. Actually, you like to put usually larger than that, like a higher multiplier, but for the sake of demonstration, I'll just put here 0.33. And here are the major waveform. We see the midpoint going up, down, and up again. And this is because the high side is going down and the low side going up. This is during the low side of the low potential of the midpoint. And then, of course, it reverses. We have some dead time here, so that we first turn off the low side and then we turn on the high side. And this is to avoid the shoot through, of course. And then we see here the charge to the gate going up here. You see it's about 100 nanocoulomb in the simulation, which agrees very well with the datasheet. And here we see the capacitor, the Bootstrap capacitor, being charged as the midpoint goes down. Here it is charged. This is the charging current here. So everything looks as we understood earlier, the midpoint going down, the capacitor being charged, but there are some other phenomena that we have to explain. I think we should understand everything that is happening here. And the first thing is this rise here. All of a sudden we see that at the end of this on time here, toward the end, we see this charge. But before that, let's have a look at the drop. The drop during the charging of the gate, here the charging is 0.35. We assumed 1 volt for 0.15 microfarad. We have twice the capacitance, so it should have been like 0.5 volt or a little bit lower than that because it's 3.3. So we are pretty close, I would say, between the simulation and the calculation. So it seems that we are okay. So now, what about this extra rise, which is associated with extra charging of this capacitor? It really happens during this dead time here, when the low side goes down and the high side, before the high side goes up. During the dead time, which we need to avoid shoot through, the transistor is off and the current goes through the diode. So there is a voltage drop. It's about -1 volt. So now, all of a sudden, the charging voltage of this capacitor is not just 12 volt, but all of a sudden it becomes 13 volt. So it starts charging again. But the dead time is short, so it doesn't finish charging. It sort of stopped halfway, I'd say. The diode is still conducting, but it is charging to a higher voltage. So I'm showing here now this in a expanded scale here. We see the midpoint going down here to about -1 volt. We see the charging current of the capacitor, and we see the capacitor starting to go up. Okay? So this explains this extra hump in this capacitor voltage. But there is another phenomenon here. There is this spike here. So why is this spike all of a sudden? See that this spike coincides with the midpoint going up. Okay? So why is this? Well, as we have said, during the time that we had here -1 volt, the diode was conducting. It didn't finish conducting. It's still conducting. And then all of a sudden, this voltage goes up, the midpoint, because the transistor is turned on at the end of the dead time. So we have a conducting diode, and the voltage now goes up, so there is a reverse voltage on the diode. So there is a reverse recovery phenomenon. There is a current, negative current going through the diode because it was conducting, now it's not conducting. And consequently, we are going to have a spike here. And this spike is going to get into this power supply, so you have to worry about it. And this is why you need a diode, which is a fast diode. And charging by itself, if it finished, will not require a fast diode. But since we have this case in which the diode is conducting and then we are reversing on it the voltage, then the reverse recovery could be very high if this would have been a slow diode. So this is why you need a fast diode. Now, up to now, we assume that the stray inductances are low, very low, or zero, okay? Now, to be more realistic, I'm adding here some inductances, 2 nanohenry, which is kind of reasonable, to these two sections. Of course, there are much more inductances in the circuit, like here and here, everywhere, okay? But let's concentrate on these two and see how much harm these are actually doing, okay? So now I'm running it, as before by the way, with a large resistor. Usually like to turn off the transistor fast, turn off fast, but in this case, I'm just for the demonstration, I'm starting with a larger resistance. Later on I'll go back to a small resistance. So we have 15 ohm here, we have 2 nanohenry here, we have 1 ohm here, and let's see what's happening. Now the main difference is that here we see oscillation. Well, oscillation makes sense because we are interrupting the current, there are capacitance of the transistors, and therefore there is oscillation of frequency that is dependent on the inductances and capacitances, so it will be in the megahertz probably range. Here it is. But the thing we have to worry about is this spike here. Okay, we have all of a sudden these spikes here, and what we see is that during this spike, the Bootstrap capacitor is charged. This is the current of the Bootstrap capacitor, and here it is charged, and lo and behold, it is charged now to 21 volt. Well, the power supply is only 12 volt. So 21 for a silicon transistor may not be dangerous, but it could go even higher. And obviously for a gallium nitride, in some versions of it, this could be very dangerous. It will destroy the transistor. So let's probe into what is really happening here. We see here the dip, okay? This is now minus 30 volt in this case. And I'm now looking at the current of these stray inductances. I see this drop, the minus the IDT, and we see a change of 82 amp and a time of 16 nanoseconds. Obviously, a silicon transistor is much slower than a gallium nitride. So in a case of a gallium nitride, this will be much faster. Now, we have this drop in the transistor current, which is turning off, a drop in the inductor current, and we know that a voltage is generated, which is equal to the IDT. So the IDT is negative, and here it is, it's causing a negative voltage at this point. So this is the reason for this spike and the harmful effect of it on the Bootstrap. Because as this voltage goes down to minus, then the effective voltage on the capacitor during the time that the diode is conducting is 12 plus this voltage, plus the peak voltage, and it could be very high. So this is the explanation for this extra, very harmful voltage, extra voltage on the Bootstrap capacitor. So now I'm going to enhance this phenomenon by making the IDT even faster than that, by making this transistor smaller, the resistance smaller, and I'm also increasing the stray inductances to 5 nanohenry, which is 10 nanohenry total. It is a little bit large for a well-designed PCB, but just for seeing the phenomena, let's have a look at this situation. So here it is. It's the same, except that, of course, the dip now is much, much deeper. It's now minus 70 volt. So let's have a look in the expanded scale here. We see here down, it's about minus 70 volt. This causes the capacitor voltage to charge to 36 volt, which causes the gate voltage, the high side gate voltage, to be 36 volt, because this is the voltage which is feeding the driver of this gate. So this is very dangerous now. So you can see that due to the stray inductances, we get a negative voltage which could be very harmful. Now, if this would have been a two-channel driver, this is a high side and a low side driver in one unit, then this would be the midpoint of this driver, and the negative voltage could be dangerous for such a driver. Now, the manufacturer are aware of it. You get a information about it in the datasheet, that is how much would a driver tolerate. So you have to be careful, very careful in just silicon transistor, not even gallium nitride, that the voltage that you generate does not exceed the maximum allowable negative voltage for the midpoint of a high side, low side driver. So this is just a side note here that one has to be careful about it. So let's now check some numbers to see if we can really understand and sort of quantize what is really happening here. Now, we have found that the IDT here is 106/18 nanosecond. This is the slope of the current. Okay, this slope is here. So now V is L the IDT, and the IDT is this number. L is the total now of 10, it should be Henry, nanohenry. And I'm finding that this should be 58 volt, minus 58 volt, the negative voltage. I see here a much higher voltage, it's 75 actually. Now why is this? Well, it is because this is a resonance circuit, and we know that its a Q is higher than 1, so therefore there's an overshoot. So aside from this base voltage change, there is an overshoot to go to even a higher voltage. Now we are not charging the capacitor to this voltage because the time is short. You see, it's charging only during this short time, but still it maintained or got to a very high voltage, which is very dangerous. So what is the remedy for that? The remedy is to put a isolated power supply for the high side transistor, for the high side drive. Very important. Highly recommended for fast transistor like gallium nitride. Now this actually releases us from all this story of this negative. It could be negative, it could be positive, doesn't matter. If this isolated power supply can support a high dVdt between the two sides, then and high isolation voltage, then it's okay. One thing you have to worry is about the capacitance between the primary and secondary, and the reason is that you have a fast dVdt now here, and this dVdt will cause injection of current into or through this transformer into this whole circuit here, which could mess up this control. So therefore you like to have a transformer with as small as capacitance as you can, and we are talking about few or even 1 picofarad. Okay, this is the capacitance that you really like to shoot at, and there are some transformers that are okay and they have this type of a specification. So this brings it to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.